This work I'm going to be talking about is basically around an 8-year-old project now with co-authors Shuchi Chawla, who's a professor at University of Wisconsin-Madison, and Dennis Nikopeloff, who's a professor at University of Virginia. I just want to give you some motivation. My background is a computer scientist. For computer scientists considering economic questions. I view one of the grand challenges that computer scientists are going to be trying to solve over the next 20 years as trying to understand how to design and guide computations that happen in the wild, not just computations that happen in digital computers. And a key computational primitive of computation in the wild is local, individual, and strategic computation happening by individuals who are participating in a much bigger system. And so what I'd like to be able to do is understand how to make the rules of a system so that when individuals locally optimize for themselves, that system produces good global outcomes. So I would like good global outcomes, and I have a computational primitive, which is local optimization of individuals. So this is, I think, a grand challenge for computer science. We've come a long way in over half a century of research and practice of computer science and being able to get digital computers to do what we want. And I think the next big challenge will be getting computation happening outside of digital computers to do what we want. There are a couple, that's a sort of a long-term goal, and at the short-term, what we can work on now that's going to be stretching towards that goal is understanding online markets. So online markets like Uber, Airbnb, Twitter, Stack Exchange, Tinder, any of these marketplaces where users come, interact, and leave, and some market mechanism mediates who gets what. Okay, that's what I mean when I say online markets. And again, this is an example situation where local optimization of individuals, the users in the system, are going to affect what happens, the outcome of the system, who gets what. Okay, and so what's nice about, I think, this grand challenge is that there's a long-term vision which I think was going to really shape a lot of policy, economic policy, et cetera. But we have a application right now that's very important that we can start making progress on. Okay, so I'm going to start just go over sort of a simple interaction that might be happening in one of these online marketplaces. Okay, and this will be an interaction which is a first price auction. Okay, so I have bidders which I've numbered 1 through 4. I'm imagining that bidders have a value in their mind that they're thinking about their willingness to pay for something that we're selling in an auction. There's an auction which is going to solicit bids, and bidders might not just report their value to the auction. They might try to, game the auction to get a good outcome, so they're going to send some other bid into the auction. The auction's going to decide on an outcome, who wins. In this case, the bidder who bids 6 wins, and what the price they should pay is. In this case, the bidder who bids 6 pays 6. Okay, and this is actually a canonical auction, the first price auction, where bidders submit bids. The winner is the bidder who bids the most, and they pay their bid. Okay? The key thing to notice here is there's an auction who's deciding what the outcome is, but the bidders are deciding what input to give to the auction for it to determine the outcome. And if a bidder changes their bid, a different outcome can come out. So bidders are going to be thinking about how should they optimize their bid in this auction to get an outcome that they prefer. Okay? Now from a computer science, that was what I just said. Note the input affects the output. From a computer science perspective, this is going to suggest that we need to rethink classically how we think about algorithms in computer science, which is, again, taking inputs and getting outputs, to take into account the fact that the bidders, the users of the system, might manipulate the algorithm to get an outcome they prefer if it's in their best interest. And if you want the algorithm to produce good outcomes, you have to reason about that manipulation as well. So you have to rethink classical algorithms. And this has resulted in a field that's been under study for quite some time, almost 20 years now in computer science, called algorithmic mechanism design. We also have to rethink how we use data to figure out how to better tune our algorithms. And that's actually the subject of this talk. And it's been a relatively new topic that people have been thinking about in computer science. It's got a long history in economics. The subfield of econometrics studies this topic in economics. And my co-author, Dennis Nikopelov, on this work is an econometrician. Okay, so you've probably seen search engine advertising. If you go to Google, you can put in the search bar search advertising, and you'll get a bunch of organic results on the left, and on the top and on the right, you'll get these advertisements. Okay, what I want to draw your attention to on this slide is I put in search engine advertising and got one ad on the top, which is called the main line. I can do an almost identical search for search engine marketing, which is basically the same thing. It's a synonym. But you'll see that I got 3 mainline ads here. Okay. Why 3 mainline ads? Is that better somehow? Good. So I want to think about this question that Google might have been facing, which is when someone does a search for search advertising or search engine marketing, how many mainline ads should we show? Okay? And so how might Google study this? And I probably don't need to tell this audience this, but a lot of tech firms and marketplaces these days use A/B testing to evaluate design decisions they could make in their platform. Okay, so I just want to walk through a sort of canonical example of A/B testing for this question. Okay, so A/B testing is basically what a scientist would call a randomized controlled trial. Okay, you take your traffic, you split them into 2 groups, A and B. You show A, the original design, you show B, the treatment design, and then you compare the results across those designs to see which design is better. Okay, so let's first consider the question of, suppose I want to estimate the likelihood that the user clicks on the top ad when there's 1 mainline ad and when there's 3 mainline ads, to see which one has maybe a higher click rate of the top ad. Okay, well that would be a pretty simple A/B test. The user searches. When the user searches, we randomize to show them either 3 ads or 1 ad. Right? The user sees that whether there's 3 ads or 1 ad, and then they make their decision. They either click or they don't click. Right? And we do this for a million times, and then we measure click rates. Let's suppose at Google we care about a different objective, which is the revenue of the auction. Okay? And we want to try to walk through the same framework of A/B testing to estimate the revenue of the auction. Okay, here, the advertisers actually bid in advance of running the auctions. They've got their bids already in place. A user shows up and sees a random page, A and B. The user makes a decision, and an outcome is reported maybe at the end of the month to the auctioneer. Okay, so I want to note that there's a problem with this latter A/B test. And the problem is the behavior we're trying to measure, namely the advertiser's behavior, the revenue we get in the auction. That behavior might change if the advertiser knew we were running with 3 mainline ads or 1 mainline ad. And so if that behavior changes, but the bids are coming in advance, then the A/B test is not first doing a treatment and then observing a behavior. It's first there's a behavior and then it's doing a treatment. And so the randomization is happening at the wrong time in the story. Okay, and so in fact, these bids probably are not bids in either A or B. These are bids that we would expect to receive if we were running a randomized experiment where some of the time we run A and some of the time we run B. And in general, in these online platforms, the advertisers are responding to these bidding scenarios where they don't really know what's going on, but they are optimizing their bid based on what they get. And so you can assume that their bid, you would hope that their bids are sort of in best response to what's happening. Okay, and so if you're doing an A/B test, it's a reasonable assumption that bids are close to best response for the A/B test you're doing and not for some other mechanism that you were doing last month. Okay, so that's the sort of difference that happens in auctions versus click-through rates with A/B tests, where things go wrong. So just to be a little bit more precise, so I'm going to just describe very briefly one of the canonical models of auctions in this scenario, and I'm going to take a first price version of it. So imagine we have n bidders that are advertisers, n positions. These are on the side of the page that you saw. The bidders are going to be assigned to a position according to their bid, and then if a bidder is clicked on, they pay their bid. Okay, and here I've shown the decreasing click rate. So if you get slot 1, you have probability W1 of being clicked. If you get the lower slots, you have lower probability of being clicked. So this is A with 3 mainline ads. And you might imagine if I had B with 1 mainline ad, that the click-through rate for the highest guy goes up a little bit, but the other guys all go down because they got pushed to the sidebar. Okay, so if my actual auction is a mix between A and B, then actually what bidders are looking at is this mixture of probabilities of click-through rates, and they're bidding in that auction that has this mixture probability of click rates. Okay, and you wouldn't expect the bids in all of these auctions to be the same. They're going to want to put different bids in these auctions. And so if you want to know what the revenue would have been for auction B, but you have bids in auction C, you might be calculating things incorrectly. Okay, so I want to go through a very explicit example of this in a much simpler scenario. So I'm going to look at a situation with just 3 bidders. Again, highest bidders are going to win, and I'm going to have the winners pay their bids. But I'm looking at 2 scenarios. One is the 1-unit auction, so I have 1 item to sell. The highest bidder is going to win and pay their bid. That's auction A. Auction B is 2 units, so the highest 2 bidders win, they both pay their bids. And auction C is going to be the A/B test that mixes between these with 50-50% chance of each one. Okay, so in other words, if you're bidding in auction C, if you bid before you know whether we're going to flip a coin and it's going to be A or B, then if you're the highest bidder, you win with certainty. If you're the second highest bidder, you win with probably 1/2. And if you're the lowest bidder, you lose with certainty. Good, so I want to investigate, and this is basically simulation data. I want to investigate what's going to happen here if you were the auctioneer and you're trying to evaluate your data to see what's going on. You want to know whether auction A or auction B has more revenue. What you ran was auction C. Okay, so here I have simulated bid data where I've drawn out each auction and I flipped the coin to see whether I ran auction A or B. So you can see auction 1 was auction A. A was a 1-item auction, so the highest bid wins and pays their bid. And you see that the revenue I got was 74 cents, and that was because 74 cents was the highest bid. Okay, on the other hand, auction 3 was auction B, so the highest 2 bidders win, they both paid their bid. And you can see auction 3 had a revenue of $1.53, which is the sum of the highest 2 bids, the first and second bid. Okay? Good, so I totaled up all the average revenue on the bottom for 200 simulated auctions. Good, and my question is, which auction is going to be better? Okay, and now I came to this work and this question from talking with Microsoft's ad auction group for over the course of many years and asking them how they looked at this question of how they dealt with their data. And talking with them and talking with other groups, people at Google, et cetera, you get started to think that they're doing something like this. Well, why don't we just look at the times we ran A and sum that up, and look at the time, or average that, and look at the times we ran B and average that. Okay, and then we'll get these averages here. Okay, so if we ran A, our average was 0.75. If we ran B, our average was 1.19. Okay, and then from this, you might conclude that auction B is better. But I want to point out that auction A, what is auction A doing from an algorithmic point of view? It's finding the highest bid, and that's its revenue. What is auction B? It's finding the highest two bids, and that's its revenue. And the bidders are bidding, not knowing whether it's auction A or auction B, so the same bids come in whether it's A or B. So summing the highest two numbers is always going to be better than summing the highest one number. So this sort of improper A/B test is always going to conclude that auction B is better, no matter what. It's always going to conclude that. And that story, that if you do these sort of improper tests of like you have bids that are in equilibrium for a mixture of our mechanisms, and then you ask, well, what would have happened if you just did one or just did the other? Or you do a back-of-the-envelope calculation where you have bids for one mechanism, but you just simulate another mechanism on those bids and see how it does. Typically, these calculations will end up with one auction that's always the best because you aren't changing the bids in response to the auction. And so this improper A/B test will always show that A is worse than B. However, since I simulated this, I actually know what would have happened had we run A or had we run B only. And in that case, the bids would change. And so I simulated the correct bid that would have happened in just A or just B. And in fact, they get about the same revenue. Okay, and what's happening in this A/B test is there's some missing information, right? The auction B is summing more numbers, but because auction B is allocating more items, there's less competition, so bids should be lower. And this improper A/B test is not taking into account that bids should be lower, and so it's going to make the wrong conclusion. Good. So that's the sort of motivating example. The statement is if you just use data that you have and simulate different algorithms with them, when you expect this data to be game theoretic, to be strategic, then you are probably going to make very wrong conclusions. Okay? So if you have data that's strategic and you want to evaluate how other algorithms or mechanisms are going to work on this data, you need to think about how people are going to change their behavior based on the different algorithm as a fundamental thing you must consider, or you're going to get the answer wrong. Okay, just an outline of the rest of the talk. I'm going to overview some of the results that we have on how to do this properly. I'm then going to review a couple areas of economic theory just to give you an overview of how those kinds of calculations go. Both the economic inference, if I observe bids in an auction, how can I infer the values that generated those bids? And then how to estimate auction revenue. If I know the values of bidders, how can I estimate what revenue I expect to get? I then am going to tell you about how to combine these two areas and to estimate revenue directly from bids in a correct way. Okay, so here's an overview of the results we're going to talk about today. And so I can talk about how good these work in terms of how much data you need to get these results to work, I just want to define a couple of parameters. So imagine we have n observed bids from an auction. And this auction is going to be a position auction like the ad auction we saw on the previous slide. So there were a bunch of advertisers on the side. So little n positions. So that was in the ad auction example like 10. I'm going to run auction B with some probability epsilon. Okay, so I'm imagining most of my traffic is going to auction A, 1 minus epsilon probability to auction A, and then I'm going to run auction B with some probability epsilon. Okay, and I'd like to estimate the revenue of auction B so I compare it to auction A. And you'd expect that the smaller epsilon is, the harder it's going to be for me to estimate auction B because I've got less data from auction B, for example. Okay, so what are the results I'm going to talk about? I'm going to tell you how to estimate the revenues of both auction A and both auction B from bids in another auction C, which is the mixture of auctions A and B. This revenue estimator is actually quite a simple object. It's just a weighted order statistic. What does that mean? That means given the environment you have, you can compute a bunch of weights. And you take the bids and you sort them, and then you multiply the top bid by the top weight, the second highest bid by the second highest weight, et cetera. You sum them up, and that's your estimator. Okay, so it's just a weighted order statistic. If you want to analyze the error in terms of the size of your sample and other parameters of the environment, it has this functional form. Note in this functional form that it has the standard dependence on the number of samples, square root the number of samples. As you know from the law of large numbers, that's the rate you expect to have when doing statistics on data. But one thing that I want to point out to you is the dependence on epsilon is log 1 over epsilon. Okay, and as you know, logs get big very, very slowly. And so 1 over epsilon, which is getting big as the smaller you make epsilon, is going to grow log of that is going to grow very, very slowly. Versus if you actually did a real A/B test, a real randomized controlled trial, what would your error be on estimating the revenue of auction B if you actually had some of the advertisers bidding in auction B and some bidding in auction A, and they knew which auction they were bidding in, so they could put a different bid in those auctions? Well, if you have capital N total bid samples and an epsilon fraction of them went to auction B, then you have capital N epsilon bids in auction B. And you expect your error to be something like square root the number of bids you have, right? So the usual error you get from an ideal A/B test has a rate of 1 over capital N epsilon, 1 over square root capital N epsilon. And so you can now compare the dependence of epsilon of these two methods. And you'll notice that the method where we use this weighted order statistic approach actually has much better dependence on epsilon than you would get with the ideal A/B test, which means you can actually simultaneously evaluate many auction formats at once because the dependence on epsilon is so small. Okay, you might wonder why you can do sort of better than ideal with the methods that I'm going to talk about. And the reason why you can do better than ideal is because in the ideal A/B test, you only ever get to see bidders responding to B when you run B. But if you mix between two auctions, A and B, and then everyone bids in response to the mixture, then every bid has a little bit of B in it. Okay, and that's why you're able to get a better dependence on epsilon than you would ordinarily. Whether epsilon was less than 1/2, and there's a little bit of a symmetry between A and B when epsilon equals 1/2, and so I've just defined B to be the one that has the smaller probability. Okay, so epsilon would never be more than 1/2. All right, I want to show you this error bound and also some simulation results on what the error actually is, so you can evaluate how good this bound is with what we actually see on data. And to show you the simulation results, I've normalized the error by root n so that you can see how the low order terms are behaving. Okay? So in this plot, I show the number of samples getting bigger as we go left to right, and the number of agents in the auction getting bigger as we go down. Okay? And so if you look at any row, that's a fixed number of agents, and you would expect that the numbers in this row, once we normalize by root n, to be about constant. Okay, and so you see these numbers are about constant as you go across every row. Moreover, if you look at this bound, you expect the number to be getting worse as you have more agents in the auction. However, in our simulation results, we're not seeing that effect. And so it could be that effect is not there, and this is just our analysis that gives you this dependence, linear dependence on n. Okay, so this is what we see. And one of the things you'll notice is that even with very few samples, we're actually able to get pretty good estimates. Okay, so with just 10 samples of the bid distribution, you're able to estimate revenue, and this is, again, normalized by root n, so that's about a quarter. So about a quarter accuracy. Okay, and so one of the nice things about the method we're going to talk about is it actually gives you not too unreasonable results with very little amount of data. Okay, great. So as I said, with that overviews the results we're going to talk about. I'm now going to talk about how you do the main two pieces are going back to the economics literature and trying to understand how we do inference, meaning if I have bids in an auction, can I figure out what values of bidders generated those bids? Because if I want to know what would happen in some other auction, I expect bidders to change their behavior in some other auction. So I need to know what their values are so that I can then solve for what they should behave in the new auction. And once I have their values and can solve what they behave in the new auction, I can estimate the revenue of what they, the revenue that would generate, for example, in the new auction. Okay, so I'm going to talk about inference. So I want to, if I observe bids in an auction, I want to infer what values the bidders might have had to bid those bids. Okay, and the assumption I'm going to make is that bidders had actually correctly optimized their bids. In other words, they're happy with the bids that they made. So in other words, if you look at the bidder's bid optimization problem, their bid is optimizing it. Okay? So, and then the observation is, well, what are they optimizing? Well, bidders are optimizing their bid to trade off if it's a first price auction, right? The higher you bid, the more likely you are to win, but the more you pay. So high bids are good because you win more, but they're bad because you pay more. So you've got a trade-off here. So bidders are trading off this bidding more versus winning more. And notice that the bidders are competing with the distribution of other bids in the auction. Okay, and the key insight that drives economic inference is the bids of the other bids in the auction are observed. Okay, we see the bids of the other bidders because they're in the data. Okay, so I know exactly what the bidders are trying to optimize. They're trying to optimize their bid, and the competing bid distribution is in the data. Okay, so again, going back to that simulation I had in the very first couple slides where I had 200 auctions with A and B, I plotted out the competing bids of bidder 2 and bidder 3. Okay, and I sorted them. And over 200 auctions, this was what the distribution of competing bids of bidder 2 and bidder 3 actually were. Again, those are the data. Okay, and I can ask, well, for any bid that bidder 1 puts in, what is the probability bidder 1 wins when bidder 2 and bidder 3's bids are random bids from this distribution? In other words, when bidder 2's and 3's bids are randomly drawn from this set of bids that I saw here. Okay? And I can plot that, and I get this function. So this function tells me the probability of winning. Okay? And now I can consider bidder one's trade-off. Remember, the higher they bid, the more likely they are to win. And you see this probability of winning is going up. But they also have to pay more the higher they bid, because it's a first price, it's a winner pays bid auction. Good. So I'm given the bid distribution, and from that bid distribution, I can solve for what the bidder's strategy is. Suppose the bidder has any value V. What is the best bid for a bidder with value V to bid when I have that bid distribution? Okay, and I can get a mapping from values to bids that would be optimal. Okay, and then I can say, well, what did the bidder bid? Let's invert that function to figure out what their value must have been. So I want to walk through this as a simple example. Okay, so how should bidder one bid? And so let's just try to calculate out. Suppose bidder's value was V and they bid B. What's their utility from doing so? Okay, and this was the data that we had before, and the data actually looks almost like a 45-degree line. Okay, the x equals y line. So I'm just going to assume it's the x equals y line, so I can do simple calculus instead of the numerical calculation. Okay, so what is the bidder's utility with value V and bid B? Well, it's a winner pays bid auction, so if they win, they get V, but they have to pay B. So their utility is V minus B times the probability they win. Okay, and the probability they win with bid B, well, it was just the x equals y line, so that's just B. Okay, which I can then say, well, if this is my equation for utility, what is the optimal bid that a bidder makes with value V? And how would you solve that? You would just take the derivative with respect to B and set it equal to 0 to optimize what value optimizes this equation. Okay? So if you did that, you would determine that bidding half your value is optimal. Okay, so if your value was 12, which is what we had in the first example, the very, very first example, bid 6. Okay? Moreover, if we observed your bid in the auction, we actually now know what your value must have been. Because if you're bidding half your value, which is optimal, then if we observe a bid, then your value is twice that. So now I know every bidder's value in the auction. Okay, so we saw that the bids were uniform on 0, 1. Well, if the bids are uniform on 0, 1 and values are twice bids, we know that values are uniform on 0, 2. Cool. So that's the first part of the economic analysis. Okay, we infer the value distribution, and now we have the question of, okay, now that I know the value distribution, how do I calculate the revenue of auctions? Okay, so I want to now take a digression into auction revenue analysis. So given, again, think in your mind, the values are uniformly distributed between 0 and 2, and I want to evaluate the revenue of auction B and auction A so I can compare them and see which one has a higher revenue. Okay, so I'm going to use the following result, which is one of the most famous results in auction theory, Roger Meyerson's revenue equivalence result. And Roger Meyerson did this work in 1981 when he was at Northwestern, actually. He's now a professor at University of Chicago. He was awarded the Nobel Prize for this in 2006. Really influential work, cited by over 3,000 papers, and essentially it drives all of auction theory. So if you know of one thing about auctions, you should know about Roger Meyerson's revenue equivalence. And that is, auctions that have the same outcome have the same revenue. Okay, in other words, if the person who wins is the same across two different auctions, then the revenues are going to be the same. Okay, so put it a different way. Suppose you want the person with the highest value to always win. Well, if the person with the highest value is always going to win, then the revenue is also determined from that. You can't get more revenue, but still have the person with the higher value always winning. Okay, so if you want to get more revenue than that, you've got to change something. Maybe don't always let the person with the highest value win. Okay? Good. So I'm going to use this idea actually to come up with a geometric way to understand the revenue you could get in an auction by thinking about very simple mechanisms. Okay? My mechanisms are just going to be posted prices. If I post a price to the bidder, what revenue do I get in the auction? That's actually pretty easy to calculate, right? Because if I post a price, I get revenue only if the bidder buys, right? And how much revenue do I get? Well, what's the probability they buy? They're going to buy if their value is above the price, otherwise they don't buy, right? So it's really easy to calculate revenue of posted pricings. And then I'm going to relate the revenue of any auction to the revenue of posted pricings just by viewing any auction as a randomization over posted pricings, offering a random price. Okay, if you think about it, bidding in the first price auction, bidder one faces a random price based on what the other bidder's bidding. And that's how I'm able to make that connection. Okay, so let's see how these calculations go. So I'm going to index the values the bidder has by their quantile, which is sort of how strong they are. So this is how we drew the plots before. Again, we sort the bidders by value and we order them and so they're increasing by quantile. So again, if the values are uniform 0, 2, then the quantile function v of q is just 2q. Because the guy with the highest quantile 1 has value 2, the guy with the lowest quantile has value 0, and it's just a straight line, right, from 0 to 2 to re-index values by quantile. Okay, good. Now what's the revenue from posting price v of q? Well, how many people what measure of people have value above v of q? 1 minus q of them do, right? Because quantile is the number of people below you, 1 minus q is the number of people above you, and so 1 minus q people buy at price v of q. So the revenue from posting price v of q is just 1 minus q times v of q. And so for the example of the uniform 0, 2, I've just written that here and expanded it. Okay, so in an auction, I can ask sort of what happens in equilibrium. Okay, I want to describe what happens in equilibrium by the following simple function. We'll just write down and try to measure the probability that the player wins as a function of their quantile, how strong they are relative to the distribution. Okay, I'm going to write that out. Okay, and I don't want to go into the details of how I calculated this, but it turns out in auction C, the auction that we have data for in the simulation at the beginning of the talk, it turns out the probability a player wins with quantile Q is just Q. Okay, it's you can work that out in probably 15 minutes of calculation if you felt like it. I'm not going to bother. Okay, and now I want to view this x of Q, this probability you win as a function of your quantile, as the CDF of a price you're being offered, as the cumulative distribution function of a random price that I offer you. Okay, and if x is the CDF of the random price you're being offered, then we know how to calculate expected revenue because we know the revenue we get from posting a price, and to calculate its expectation, we integrate the revenue for every price by the density of the CDF, or the probability mass function. Okay, so the probability mass function is x prime, that's the derivative of the CDF, and you can calculate the expected revenue of a random variable by taking the random variable, multiplying it by its density, and integrating. Okay? So again, if I do that, my allocation rule is x of q is equal to q. Its derivative is 1. Right? So my integration is integrated from 0 to 1, this formula 2q minus 2q squared. Okay, so you do that, and you get 1/3. Okay? So this is going to be the revenue from one of my bidders in this auction. I have 3 bidders in the auction. So my revenue is 3 times that, and so auction C's revenue is about 1. And if you flip back to the very beginning of the talk, where I had those simulation numbers, and we looked at how much revenue auction C was getting total, it was about 1. Good. So that is the overview of how you calculate revenue. But I now want to go to to apply this calculation to auction A and auction B to see which one is better. Okay, so let's do the exact same thing for auction A and auction B, but just to summarize, here's what we did for auction C, and I've got now a picture of what was happening with that integral. So here in the blue, I've drawn the derivative of the allocation rule, which is the density function for offering how I can view it as offering a posted price. And in red, I have what I call the revenue curve, which is the revenue I get from posting price V of Q. Okay? And I multiply those two together and integrate them, and that integral I've drawn actually is the shaded pink area. So that's a pictorial representation of the integral. Okay, so auction A and auction B, you can calculate their allocation rule as a function of the agent's quantile. I mean, the probability an agent win is a function of their quantile. Okay, and those formulas are x squared for auction A. What was auction A? Auction A was a single item auction. So why is this Q squared? Well, an agent has quantile Q. The agent wins with both the other agents are below him. What's the probability that one of the other agents is below him? Well, he's got quantile Q, so it's probably Q he's below. What's the probability both are below? Q squared. Okay, so it's really easy to calculate auction A's allocation rule. It's just Q squared. And its derivative is 2q. And so now you can plug into this integral, which I've written the formula here to calculate its revenue, and it's also 1/3. Okay, and again, I've depicted with the pink area, when I multiply the derivative of the allocation rule with the revenue curve, that's sort of pictorially the revenue I'm getting. Okay, auction B. Similarly, I calculate that. I get the allocation rules to calculate the revenue. And what you'll see, actually, is that the allocation rules derivatives are sort of skewed opposite directions. And you also see that my distribution is symmetric. The revenue curves is a symmetric function, about 1/2. And so that's actually why all the revenues are all the same. They're all 1. Right? One of them skews the integral one way, one skews it the other way, but they're symmetric skewings and they sum up to the same thing. Okay, so in this example, it just so happens that all of the auctions, A, B, and C, got the exact same revenue 1. But here's the thing. If I were to change what I call the revenue curve, R of Q, the revenue I get from posting the value that corresponds to quantile Q, if I were to change that to skew it either higher or lower, I would have gotten a different result. If I skew it lower, then auction B does better. If I skew it higher, auction A does better. Okay, so as we said at the beginning, you could generally get auction revenue A better than B, or generally get B less than A less than B, sorry. And we won't know that till we go to the data and get the valuations so that we can see whether the revenue curve is skewing high or skewing low. Okay, so I just walked through sort of a 2-step process for how to estimate revenue. Step 1, take the bids, infer values, get a distribution of values. Step 2, calculate auction revenue, and we did it using revenue equivalence here, to predict the revenue of whichever auctions you want to predict revenue of. And the great thing is once I get values, I can predict the revenue of any auction. Right? Doesn't even have to be A or B. Right? I'm done. I can do anything with that. So I now want to talk about a direct method for estimating revenue from bids. Okay, now I want to take these two separate pieces and put them together, and it's going to simplify a lot, actually. And that actually is just to tell you about what the research that my co-authors and I did. The main contribution that we brought to this project not was this. This was already known so far. Our contribution was putting them together and figuring out how to put them together to get much better error bounds than if you would have analyzed them in two separate pieces. Good. So let's talk about directly estimated revenue from bids. First, I just want to summarize what we did before. So from what we were saying a couple slides ago was, given the bids, and I'm going to write those bids that we observe as b hat, and b hat prime is the derivative of the bid distribution. So this is the empirical bids that I observe in the auction. From the empirical bids I observe in the auction, I can infer values. And I just wrote out what the general equation is for that. We did that just with the example that we saw in the data, where remember we said we write out the utility, we take the derivative, set it equal to 0, and get the function. So in general, if you did that, it would look like this formula. Okay? And here, again, the allocation rules are known because we know what the auction we ran was. Okay, but the bid functions, the b hat and b hat prime and the derivative, those are unknown and observed in the data. Okay, we then combine that with auction theory to estimate revenue, and our formula for revenue was just the integral of, and I separated it now, the revenue curve was the value times the probability of winning times the derivative of or the density of the allocation rule, the derivative of the randomized price we're considering offering the player. Okay? Good. So if you're going to do this two-step approach where you first estimate values and then plug into this revenue, then you would get the following analysis. You would get your error bounds on your bid distribution at the standard root n bounds in terms of getting error. Your error, to estimate the derivative of the bid distribution, you're going to have to use things like bandwidth functions to smooth the bid distribution so you can get a derivative. And those are going to result in you getting a worse rate than the standard rate. Okay, which is going to result in the estimator you get from these two steps having worse rate than the standard rate. So the thing that my co-authors and I observed was we can just plug these formulas in to each other and then do some simplification. Okay, and the key idea is when I plug these formulas into each other, and I'm going to get some terms that have the bid distribution there, and I'm going to get some terms that have the derivative of the bid distribution there. Everything else is known. Okay, the 1 minus q is a known function, the x prime of q is a known function. Everything else is known except for what we observe in the data, which is the bids and the derivative of the bids. And then we can do sort of one of the canonical tricks in auction theory, which is integration by parts. We have derivatives we don't like, which is what's giving us a bad rate. I can integrate it by parts to replace that derivative with its integral, which is the original function, and then a derivative of something else. And in this case, I'm replacing the derivative times stuff I know with the original function and the derivative of stuff I know. And the derivative of stuff I know is easy to calculate because I know the stuff. Okay, and so I'm going to end up with an estimator that looks like just some coefficients integrated times the bids. Okay, and this is why I say my estimator is a weighted order statistic. Okay, because what are the weights? If I have a bunch of bids, I'm going to take them and compute these coefficients I get from the formula and evaluate that at if I have capital N samples at 1 over n minus 1 intervals. Okay, and that'll give me an estimator for the bids. Okay, the hard step, of course, is to bound the error that you get. If you show these coefficients are small, you'll show your error is small. And so the hard step is basically to bound the magnitude of the coefficients. Okay, just to overview what we've done here. If you want to estimate the revenue of auctions you did not run with an A/B test, you can actually do the A/B test, and then from the A/B test, the definitions of the auctions, you can derive an estimator, which is just a weighted order statistic. It takes coefficients and bids, you sort the bids, you multiply by the coefficients, you sum that up, and you can directly estimate the revenue of auction A or auction B from your bid data. It has a nice theoretical analysis, and it works very well on simulated data. And I view this as sort of a part of a growing literature in computer science, combining with ideas in economics and game theory on understanding how we can guide and design computations that happen outside of digital computers. And so one step of that equation is, and I think a good first step of that equation is understanding how to get online markets to produce good outcomes. And in online markets, we have a lot of data from running various market mechanisms, and a key question we face is, if we're going to make changes to those market mechanisms, which changes will result in better outcomes? And that question of which changes result in better outcomes is a question where you can't just run a counterfactual mechanism on your old data. Because as I showed with my first example, typically that'll lead to one conclusion always, regardless of whether that conclusion is right. In my first example, recall auction B always seemed like it had higher revenue than auction A. Okay? Instead, you need to bring in some game theoretic analysis and some economic analysis to understand what is driving the behavior you see. Okay, what are the values of the bidders in the auction that's driving the behavior you see, so that you can understand how people are going to change their behavior when you make a change. Okay, and then you need to estimate your whatever objective you are looking at optimizing, say revenue or say welfare, in the changed mechanism with your estimate of the sort of the fundamentals of the system that's driving the behavior. Okay, so this was what I view as sort of one of the first sort of forays into how to take the data and actually make predictions you want. It shows that actually combining some of the theory from econometrics, some of the theory from auctions, you can come up with very simple estimators, which have very good statistical properties that allow you to make actual predictions about what might happen in your auction. All right, thank you.
Usually our data in auctions show that users are not optimizing their bids properly, and so we get like noisy data, and it's not logically optimizing, it's almost sometimes random. And how can we check that this approach won't suffer from this noisy data and produce wrong results?
Yeah, that is.
And so how to measure this noisy delta?
Yeah, that's an excellent question, and I want to give you two different answers to that question. So the first answer I want to give you is that the methods that I've talked about here tend to behave nicely when you add noise, meaning you can add the noise and then ask what happens to your estimates, how the noise impacts the estimates, and the noise in the estimate you get actually behaves nicely compared to the noise you added. That's one answer. Another answer, and I think, and this gets at where I think the field is going right now, and that is many of the, for instance, bidders in these ad auctions are employing search engine marketing companies that are optimizing their bid for them. And if you look at that bid data, the bids are going like up and down as the algorithms are optimizing bids for the bidders. Okay, and so a question that people have been looking at has been, well, if algorithms are optimizing bids, how do you deal with that kind of data? Okay, and so the usual economic approach doesn't work because the usual economic approach assumes that we're in a static equilibrium. We've already converged. That's the equilibrium. We're there. Okay, so a recent trend, the last 3 years, say, has been let's try to do similar kinds of things with data that comes from learning algorithms. And one of the key features that the analysis that this literature has produced so far has been that one of the key outcomes has been that you can actually do very similar kinds of analyses that you do statically to infer values from the algorithm, the data from the algorithms. In other words, for example, one of the canonical algorithms for optimizing bids looks at online algorithms, online learning, and these algorithms satisfy what's called the no regret property, which is that looking back in hindsight, the bidder wouldn't want to switch from this crazy moving bid to a single bid in hindsight. Okay? That inequality that you get, you don't want to switch from what you did to this line, or this line, or this line for every single line, is very similar to the inequality we had in our setting, which is you bid this, you don't want to bid some other bid. Okay? So you've got a bunch of inequalities which you can now use to pinpoint what the values of the bidders are again. Okay? And so the answer to your question that I like the best is it turns out that if bidders are using learning algorithms to bid, which haven't been exactly optimized, you can still use the best response property to pinpoint, not to pinpoint actually, to define the rationalizable set of values. What are the reasonable values that bidder could have had if they behaved that way?
Thank you.
Are there certain types of mechanisms which are Thank you. Are there certain types of mechanisms which have structurally better or worse rates? More specifically, if you have reserve prices, does that fundamentally change the results that you see?
So that's another excellent question. And the answer is the results that I presented here don't apply directly if there are reserve prices. And the reason why is that when you do integration by parts, you're assuming that the allocation rule you had was smooth, that derivative was defined. So if you have a reserve price, that means below that price, you get 0. After that price, you start winning with some non-zero probability, and so the allocation rule jumps, which means my derivative is not defined there, which means if I were to correctly do this integration, I'm going to get a delta there I have to integrate, and that delta is going to keep the derivative of the bid distribution. So I'm going to have to know the derivative of the bid distribution. But unlike the usual case in econometrics, where I have to know the derivative of the bid distribution everywhere, I only have to know it at one point, which is the lower bound, if I want to use methods like this with auctions with reserve prices. Okay, but it is going to change, and it's going to change the math in that at that one spot. That was kind of, from a mathematical point of view, kind of annoying when we were doing the math here. And so we restricted our attention only to auctions where the math was a lot nicer, which are rank-based auctions. So auctions kind of like the ones you see on these ad auctions, but without reserve prices. So these are auctions where you only look at the ranks of the bids, you don't look at the actual values of the bids. And if I was just going to take the bidders and put them on this page, right, and put them in the right order, I wouldn't need to look at their bids. I just need to sort them and put them in the order of the bids, and that would be sufficient. And so that actually makes the auctions much simpler to analyze. I think there are interesting questions to get beyond that assumption that we made, but that area is a little bit mathematically more complicated, so it hasn't been investigated very thoroughly.
Thank you for your talk. And I wanted to ask, are your methods applied to second price auctions? And also, second question is, if you, for example, extract valuation distributions from first price auctions, then can you apply it further? Like, this is a stupid question. Can you apply it further to the second price auctions? Are there any barriers to do this? Thank you.
Yeah, let me give you two answers to your question. So the first answer is, if you're assuming the usual economic equilibria in a second price auction, so second price auctions, as you know since you asked the question, have a dominant strategy equilibria property where no matter what anyone else bids, your dominant strategy is to bid your true value, right? So if you're assuming that bidders are bidding their true value, you don't have an inference question, right? Because you already know their true values. So you don't have to apply the methods that I've been talking about. Now, with that said, that's why I have two parts to that answer. Many of the times people employ second price auctions, second price like auctions, other things are happening. For example, in these ad auctions, Google and I think other places use what's called the generalized second price auction, which is actually not a second price auction. In that auction, bidders are charged the bid of the bid below them, rather than their bid. Okay, so it's second price like, but not the second price auction. So in this auction, there isn't a dominant strategy of bidding your value. And the econometrics of this auction are actually much more complicated because there isn't a simple closed form for that first equation. Okay, the equation that backs out what your bid must be given your value. And in fact, if I were to go back here, the problem arises. I have to go back pretty far. The problem arises here. If I want to write out your utility, in the first price auction, I can write that out really easily. It's your value minus your bid times the probability you win. If I know your bid, which I do because I observed it, and I know your probability of win, which I do because I know what the other bids are, and I can evaluate the probability you win with that bid in the mechanism, right? Then I have everything I need to calculate your revenue. Right? The second price auction is a lot more dicey to get closed form. You can still do that empirically with a second price auction, figure out what the expected payment is. But it's a little bit dicier to use in these equations here. Okay, so I do not think doing taking these kinds of approaches for the second price auction would result in very significant changes in practice. But for the theory and doing the math, it makes it more complicated.
I have a question about, maybe it's like a meta design question, but like the trend has been to introduce the mechanism for submitting the bids, right? Lately has been to submit vectors of like you submit bids for say keywords, and then you submit vectors of multipliers, and the number of these vectors of multipliers is like increasing every year. So first we had device, and now we have like gender, age, hours, and I mean, I just want to hear your view on if this complicates the analysis for the search engine of inferring what the values are, because for a search advertiser, it makes it much harder to actually translate the values into these vectors in the first place and submitting a reasonable distribution of bids since they are multiplied. So what's your view on that?
I agree that multipliers makes things complicated. What's happening in these auctions is that they're realizing that, so they're actually And I want to point out two issues that arise with the introduction of complex bidding spaces. Okay, so one issue is, do the advertisers actually have distinct values for those different scenarios? So these multipliers are to pin down, again, maybe it's ad auctions. So maybe there's demographic information with the user that comes in. So maybe you might have different multipliers based on whether the user's from Europe or Russia or the United States, right? And that could multiply by the bid that you're putting in because you have a different value as an advertiser for these different kinds of users. But another issue that comes up with these, with putting in different bids, is actually the competition for users in the United States or Europe or Russia might be different. And so there are two issues. One is the value that you get from those different users might be different, and the other is the competition for showing ads to those bidders might be different. Okay, and so I think the most important thing in the design of mechanisms is making it so that if you don't have different values, you don't have to express different values. So in other words, if someone had the same value for users regardless of whether they were from Europe or Russia or the United States, they should put in one number. But that might not be true if they had faced different competition in the US versus in Russia versus in Europe. Okay? And so that's sort of the key place that sort of dimensionality of the bid space, I think you want to think about it. You want to let people express different values being different, but people shouldn't have to express how the competition is different. Okay? It is generally true that the more knobs you give someone, the more likely they mess it up. And so I think there's definitely a design choice to be made with reducing the number of knobs if the reduced number of knobs is pretty good. Just because it's less likely that people will mess it up.